It's right. You said the computer, I don't using the device. Oh, while we wait for Prime and Max. So it's homework 3 was due today. Homework 4 I posted. It is due. There is only one question in midterm. No, that's not midterm. In homework 4, and it is a reasonably simple extension of what you did. or what I did in the last lecture. So there we had a capacitor and we calculated the force on one of the capacitor. So now we will have a current in the capacitor also, current in the sense of charges are moving on a plate. So maybe let's write that. And that's a positively charged plate, negatively charged. And the electric field is this way. That's electric field. Now let's say we have a new configuration where all these positive charges are coming out of the board. So there is a flow of those positive charges, and there is a negative charges are going into the board. So instead of this configuration, we switch and say that this is a current now. And that's, so now we don't have it. So the current carrying, so if you think of this as current, then there is a magnetic field. Right? And then you do the same problem where you try to calculate the force between the two plates of the capacitor. Okay. So
you're saying there's current going into and out of the board alongside
of the plates. And usually the current is described in terms of a velocity, like drift velocity of the electrons. So there is a velocity associated. And you can always think of a situation where the velocity is zero. In that case, you should get back your original result that we did in the last lecture. Okay. Now, I think this is discussed at certain places, but be careful with the interpretations of what is there. Be critical of whether things are right or wrong. Okay. So otherwise, just follow the whatever we did and try to come up with the case. Always think of what happens in the rest frame. If you start moving with the same speed as the plate or current, everything becomes at rest and you should get back certain results. So that's the idea of relativity in a sense. So make sure that's there is mass. Any other points you want? Okay, we'll do one more example on electromagnetic stress. We call it stress because it's force per unit area. Whatever force we calculated on the plate, it's force per unit area. Yeah, if it comes out to be that, then you say it's stress of the pressure on the plates. So we want to have one more example of that, and then we will move on to other considerations starting next week. So let's have electromagnetic stress on a spherical charge. By spherical charge, I mean a charge of radius r, where the charge is uniformly distributed on the surface of a sphere. So what you mean is let's have, we have two choices here. we can have all the charge on the surface, or we could have all this be uniformly distributed on the. This is a shell, that means charge is on the shell, or it could be uniformly distributed everywhere. When we think of a electron, let's say, is the charge on the electron on the surface of the electron, or is it everywhere inside, deep inside? Is it a solid charged sphere when we think of an electron, or is it all on the surface? Sorry.
You think of it as solid.
We don't know. Okay, so electron is we really don't know the radius of electron as of today. The deepest we have gone in distances is about 10 raised to minus 18 meters. 10 raised to minus 15 is that of a proton. 10 raised to minus 18. We don't have enough sufficient energy to go deeper. So what we know is that whatever electron's radius is, it's smaller than 10 raised to minus 18. So that's a bound on the electron's radius. We don't know. And without going deep enough, we never know whether it is spherical or not. For example, it's equivalent to asking, sitting outside the Earth's surface, do we know if Earth is hollow or a shell? From outside, it's just the mass that matters. As far as it is spherical, that's all there is to it. So there is no way to decipher the information about whether it is or the geometry of the distribution staying outside. Okay, so if charge is, let's say this is a shell, so everything is there is no charge in here, right? So this is on a shell. It's not necessary that you distribute it like that. It is easy to do that. You just say that's a conducting material, right? If it's a conducting material, difference between a conductor and an insulator is that charges are free to move around on a conductor. So if it is free to move around, they will try to stay apart, stay away from each other, right? Positive charges don't like each other. So they try to stay away from there, and it is an automatic, or it is an easy way of. So you can ask the earlier question that I raised. It is equivalent asking, is the electron a conductor or a insulating body where the charges just stay where it is. We are saying this is a conducting shell, so it is all on the surface. What's the electric field due to such a sphere? So that is a radius r. Okay, so what's the electric field due to a spherical distribution of charge of radius r?
Inside or outside?
Let's do both. Let's start with inside.
Inside is 0.
Inside is 0, so that's 0. Inside, so that's let the observation point r less than r, and outside is 1 over 4 pi epsilon naught q. The charge q distributed on it over r squared, and let me write that as q over 4 pi, and this is r over r cube. It's r hat over r squared. It is r over r cube if we are outside. How do you know that's 0?
No charges inside.
No charges inside.
In the conducting sphere, charges are on the surface. They don't.
And is there anything else you have to use? Oh,
They also cancel each other
cancel each other out. How?
because there is symmetry.
So suppose you have a sphere here at this point. You're closer to this, right? These charges are closer. How is the symmetry is obvious? Why is it zero?
Because
Going back to the lecture, you said there's no charge.
Yeah, if we consider Gauss circles to that.
Gauss's law, right? Yeah, correct. If you take Gauss's law on the right hand side, the charge is, it's an enclosed charge if I take a surface inside. And then there is an area times that it's a surface integral that comes out to be zero. So electric field has to be zero. Good point. But suppose we go back to Aryan's way of doing it. We want to do it the integral way. So we should be able to integrate all these contributions, right? This exerts a force here, right? Let's say there's a test charge, that's an electric field here. It's closer, so it is stronger. And diametrically opposite, there is somewhere here. That's actually a little weaker. It's somewhere here. Somewhere here, there is like this. This one exerts a force like this. And the claim is that if you do this integral, it is zero. How do you see that so clearly?
there is a depends on distance.
If
If it's further, it's less.
distance. But that distance is larger, right? Whatever the distance is. So. This should be weaker. Right. So how come it's. So this is weaker, so that will be, it won't balance, right? Seems like it won't balance. This is the first argument. The integration can be performed. It involves, if you appropriately do this, or in a very general way, it involves spherical harmonics. But if you choose some coordinate system, it can be done. That's one way of doing it. But there is a nice argument. It is worth pointing out, just using again symmetry arguments. But this is not a complete story, right? So let's say pick the point again and have a cone. Go this way. And this is not the center of the sphere. Center of the sphere is somewhere here. This is a cone. That means there is a. You can think of a tennis or a shell. What do you call that? The arc of a shell. Like a cap, right? Cap of the cone itself, and there is a cap of a cone here. What's the area of this cap? It's a spherical cap. What's the area? Let's say this is R1, that's R2. What's the area of a spherical cap? Or spherical cone, let's say. Is that clear what I'm asking? Okay, so let me ask this better. Okay, so this is the center. So this is radius R. That's angle theta. This is a circle now. That's S. How is S related to R? Theta, good, right? So now let's say the same thing, but now I'm on a sphere. Right, so this is a cap now. Right, so that's a cap, and now the area. I want the area A is equal to. Let's again have radius R. What's the area of that cap?
2 pi r things.
Not 2 pi r theta. Why 2 pi r theta?
What the like
Oh, which is the angle? Oh, maybe tell me.
is 2 by or if where the theta?
Two.
What is
Yeah,
the
where did you get two? So you're saying, yeah, maybe.
what is the angle?
That's what I want to leave it to you. What's the angle do you want? So here there is an angle, right? So there is a cone angle, you call it a solid angle,
Yeah.
right? So you would say it is, suppose the solid angle is 3. So solid angle for the whole sphere is 4 pi. In that spirit, this is omega, right? You would say this is omega. Okay. Where there are two angles you have to integrate on. Okay. For same fixed R. After that, what is left over? This was R. R square. Okay, which is probably correct as you're saying it is 2 pi. 2 pi times the theta. So if I think what Aryan was trying to say is that if this is angle theta of that, then you're telling phi is integrated over the usually 2 pi. So this is also equal to in the diagram that is shown there. So it's 2 pi times theta r squared. A good point. Yeah. Okay, but in general, it is the solid angle that matters, whatever that angle is. Good. Okay.
Yeah.
What that means is that this area here, A1, is equal to, that's a solid angle. These two are the same solid angles. So it's sigma R1 squared. Area A2 is equal to the same solid angle, but R2 squared. Different radius. That's important because now make this small and you have what we have is dq1 over R1 squared. That's your electric field due to the top cap. Okay, make it infinitesimally tiny angle. That's equal to dq1. If it is uniformly distributed, it is some charge distributed per unit area sigma times the area over R1 squared over R1 squared cancels out. Right, no R dependence. From the other side, you have dq2 over R2 squared, same argument. That clear? So the charge here is exactly the proportional to the radius of R square, and they cancel out. Like so, 1 over R square dependence is exactly cancelled by the uniform charge. So because of that cancels out. So that's a simple symmetry argument that I think you were trying to mention. Yeah. So the electric field is 0. And same argument for gravity. If Earth was hollow, you jump inside, you don't experience any force, you won't get attracted to the surface, you will feel weightless inside a hollow. Okay, so that's electric field. Question?
It's also kind of similar to planet's orbit. If you imagine circular orbit,
Inside,
say, a comet orbiting around, or the Earth orbiting around the sun,
Tell us again.
kind of like you can do the same process as what you did now with the cones. You've got a circular orbit.
Yeah,
and
I think there it is the conservation of angular momentum that comes in. This is Kepler's second law you're thinking of?
Yeah, Kepler's second law.
Correct. There, that leads to the idea that that a planet will go faster when it is closer to the sun,
Yeah.
and slower when it is farther from the sun because angular momentum has to be conserved. Good point. Yeah, it's a very similar argument where you talk about the cone area that is but there it is planar. Yeah, so that's a little bit of simplicity because planet moves in a plane. Yeah, good point.
Okay.
Yeah, good point. Yeah, very similar. Yeah. Okay. So what we have is, so that's your electric field then, correct? Symmetrically outward. And intuitively, it is clear that this is a shell. If this was elastic in nature, this will enlarge, right? That is a repulsive nature to this configuration, and which means that there must be a stress on it, there must be a pressure on this. If you try to calculate this again, naively, you would get that, oh, this charge has to repel this charge as you get closer. It is so close to each other that it will diverge. So that will be your initial expectation, and we won't even try that. But let's do this using our methods that we have developed at this point. Let's talk about the conservation of linear momentum. We have partial derivative of electromagnetic momentum density plus the divergence of the flux of momentum, right? and plus the force density is equal to 0. This is all a local statement in the sense that each of this quantity is having a position and time dependence. Right? There is no time dependence in this whole problem. Or what is the magnetic field associated with this? With for spherical charge distribution, magnetic field 0, right? So unless you start moving it, move this charge, at least in a frame, if for an observer, for whom this is at rest, that's equal to 0. And remember, G was equal to B crossed with B. That's equal to 0 immediately. So the first term is 0 to begin with. So you can say the force density is equal to minus the divergence of G. The expectation is that things will be radial. That's the expectation. But if I have a radial quantity, let's say R hat, and if I integrate over a volume, E cube R, centered on a sphere about volume about around origin, let's say, sphere around origin. What is that equal to? Vector R hat if I integrate on inside a sphere.
The volume.
Yeah, so let's say this is. So this is the center. So at every point here, there is a R hat, right? On inside a sphere everywhere. So I want to integrate it over a volume of radius R, origin, around origin radius R of R hat. It's a vector. For every point this side, there is another point here, right?
Yeah.
Here. Here. But symmetry will be 0. So, in a sense, if you think of this as a force density, if I calculate that, that will come out to be 0. But that's still, we understand that that's equivalent to saying that this is moving this way. There is a tendency of force going that way. But that doesn't mean that there is no force on a region. So we want to talk about force per unit area. You want to get away from that directional cancellation. So let's calculate F dotted with R hat so that you only have the magnitude of this coming out. And that will be equal to, notice this is a dyadic. Then I have to multiply on the right side. That's minus of. Now I have to be careful, the gradient is operating on T. I don't want it to act on R hat, so remove that. So this parenthesis means that the gradient acts only on T, not on R hat. Now, the total force, the radial force, if you want, on the sphere will be defined as, so this is a scalar quantity. This is a radial force on the sphere. Right. In that sense that you take it at every point, you calculate that force, add it up, that will be defined as the volume integral E cube R of F dot with R hat. I need to specify the volume V now. So the volume V will be a tiny bit of a sphere beyond R, so this is V is of radius R plus delta, where delta is time. It is slightly, it's almost hugging the sphere R from the outside. Okay. If it is inside, what will this integral be equal to? If I had written R minus delta, what would be F? F would be starting from here, there will be a T dependence. T, remember, has electric and magnetic fields. But electric field is all zero inside. So there is no flux of momentum. So nothing will be there, it will be zero immediately. Right, so there will be, and no tendency for it to, so, and that is no material here, if you think, then there is no tendency for that. If there is a conducting material, at least there is no electromagnetic stress on it. So let's come to the right hand side. Remember, I should clarify that T is equal to a unit diatic times U minus E times D minus of H times B. Where U is equal to half dotted with D plus half. There is no magnetic field zero, so this term goes to zero, this term goes to zero, right? So this is, that term is not there. It's still. Not there. But we'll come to that again. Let's calculate U to begin with, and we have to process this also. We have to do this integral, right? That's what we have to work on, or maybe I should say, since this is equal, so this is equal to d cube R, and it is good to immediately write this as hat. Again, remember, gradient acts only on T and the R hat is outside, right? The dot products are, because there is two vectors, hopefully by now we have used this sufficiently that there is some clarity in what, or there is an intuitive feel for that. Yeah, that's a volume. Okay.
So better here if we first use the T dot R and do the integration. Do the del.
You
Or
mean
do
to
the
say
delta T and then R.
that
The
again?
difference. So the difference if we do delta T dot R or T dot R and then.
It matters because the gradient acts only on this, it does not act on. Right, so for example, let's do this. So let me leave this a little for later. Let me come back on this. Okay, so that is the radial force as a scalar quantity. This is equal to d cube R times gradient of T. The same, doesn't matter which parentheses I use, and that is the R hat. If you recall how we proceeded in the earlier case of a capacitor, at this stage we use divergence theorem. Right? What does divergence theorem give you here? Be careful. Like remember, divergence theorem tells you dq gradient. Typically, you work with a vector, right, when you're doing divergence theorem. So let's say A, right? There's some A here around. There's some random vector A that's equal to dA dotted with A. And now this is on the surface. Right? This is on a volume, that's on a surface enclosing this volume. The whole, if you go back and look at this derivation, the main idea is that this is a boundary term and there is a derivative that cancels. This is pretty much in one dimension. This is the same as saying d by dx of f of x. Let's say this is A to B. This is the, if you think of a one dimension, what's the surface of one dimension? If you have a curve, what is its surface? That question is clear. A volume is bound, yeah, maybe the word is volume is bounded by a surface. What is a curve bounded by? Curve is bounded by points, right? The line will be bounded by points. A volume is bounded by a surface. So a volume is bounded by a surface. So the same argument here, a curve will, this is on a line, we integrate, is bounded by the points. So you say this is f of b minus f of a. These two are pretty much same, but this is a region, so it is the more elaborate way of proving it, but the content is pretty much the same. Yes.
Now the tensor T be written as that, like we can change the tensor product. DE can be written as ED.
Yes, here we can, in general, you mean here or there?
There.
There, right? In general, no. So for example, if you have an general operation M and N, or M and N, this is not equal to N and N. Think of it as indices, M, this will be Mi and J. Right, so this is M1 and 1, M1 and 2, and let's make it two-dimensional long. And this will be M2 and 1, and M2 and 2. Right. On the other hand, if I do this way, this is M N. Right. NM would be do the same thing, it will be N1 M1, which is the same as this. But this need not be the same, right? N1 M2 M2 M1 M2. So it's exactly opposite, but it will be the same if N and M are the same. Because then it doesn't matter where you are. Right. And what we have in our situation is E times D, that's equal to epsilon E times E. These are the same vectors. Right. So because of that, it is true that, and this means that it is symmetric, right? There is a symmetry about this diagonal. So you can show that. So a general question is P, the flux of momentum, is it symmetric or not? That means, is it component wise, non-diagonal terms, is it the same as Tij minus Tji? So that's 0 because of the symmetry. Does that answer the question? Is that clear? Okay. And for that reason, it is okay to write DE or ED, it doesn't matter. Sometimes I write it this way, sometimes I write it. Okay. So this is true, but we have now generalized this for a dyadic. And that is a dot r hat now. But this is true only when it is really on the boundary, right? This has to act on everything on the right. So divergence theorem cannot be used immediately here because it is acting only on partial terms. It is not a not a total derivative. Like integration is an inverse of derivative only when it is total. Right here, it is not really total, so you have to process this a little bit. Let's process that. That's equal to integration by parts, right? If you have two functions, so think of t as one of the functions, r as another function, and do integration by parts. So this is minus integral. Or let me do one more thing before, maybe it will help. Let's write this as indices. It should help. I, T, I, J, and R hat J. Is that clear? Like we have used index notation, so this is the same as the. Is everyone comfortable with it? Abdullah, have you got used to the index notation? Yeah, or you're still. I'm still learning. Okay. Yeah, because I think you were not in the math methods course, right? Or did you take math methods? Yeah, I think, but that's okay. Yeah. Okay, so try to get used to, okay, so, but this is not a total derivative. I can do integration by parts. This is the same as d cube r. And notice what I'm doing. Instead of r hat j, I apply on both. This means that this has to act on both. Right? But that's not correct because it is supposed to act only on t. So this is not the same. So subtract out whatever is the wrong part of it. So minus, I have to pitch on the other one, right? So it is Tij times r hat j. Is that clear? So this is like distribution, right? When I hit here, this will hit this, which is the answer. I have an extra piece that I get when I act on this. I subtract that out. Is that clear what happened? Okay. This is symmetric. I think Manuka asked a question about E and D. I argued that D is symmetric. So I can swap this Ij. Right. So Ji is the same as Ij. So I write this as Ji. Okay. That has this feature that this can be interpreted as a dot product. And J in the outside part is also dotted. Remember, that is a trace. When the outside vectors are dotted, it is a trace. Maybe go back. And if you have a matrix M dotted with N, that's a matrix, that's the same as M I J and J K. But if I write trace of MN, there were some homework problems emphasizing on this. This is the same as when you set I equal to K. K, so MI and J. Sorry, MIJ and NJI. Is this clear? Because they are the diagonal elements. So think of this as a whole matrix. So maybe a K. It's another matrix. And the trace of that will be the diagonal elements. So this will be IK. IK. Okay. And J is got by multiplying. So trace of a matrix is basically the diagonal element sum. So this is simply I and K that you trace it out, and that's I that you get. And that's the same thing that is happening here. I is dotted, J is dotted from the outside, that means this is the trace of this two dielects together. We want to put that together, so let me write this again. This is d cube r, gradient operator. So now I'm first taking the dot product with respect to r hat, and then taking the gradient of the whole. Right, there's a difference between this and this. But it involves cube r, again a volume integral, and this is the matrix T or the dialectic T dotted with a dialectic acting on r hat, and then take the trace of the like, make sure you get this argument there where you're converting that into a trace. Okay. Like I'm flipping from dyadic to vector index notation, or temporarily I introduced that index notation just to clarify this distribution under differentiation. This is now a surface integral. I can use divergence theorem here. I cannot use divergence theorem there. Right, because this is a total derivative now. It's acting on everything that's in here. That's a vector basically. It's a total vector. So this becomes a surface integral. So this is dA. The surface of this is a sphere. So I say it is r hat dotted with T dotted with r hat. Like this was actually a vector here, but that is only in the r hat direction because of my particular surface, which is spherical. And then I have twice a volume integral of T the trace of this. The thing. Let's do a little bit more processing. Expect it to be faster. What is gradient of r hat? Anyone?
Was delta.
One. I think you guys are thinking, sorry, yeah. Like typically we say vector r is 1, right? Dyadic 1. And what is gradient of magnitude of r? R hat, right? So this is neither one of them, but I can write that in that form. So this is gradient of vector r over r, right? And this is not a dot product, not a cross product, but we can work on this. Almost immediate. This is vector r over r, and then I have to hit plus gradient of r. That's the distribution vector r. Correct. Again, there might be a confusion of order. Do I write this on that side, this side? But these are all dependent on r. However you do it, it is symmetric. If it is not symmetric, then you have to worry about it. But always in these situations, it will come out to be like that. But otherwise, use index notation. get that. In this case, it doesn't matter. This is 1. Now we know how to do this over R, and this is minus R hat over R square. Like first you do 1 over R square, and then gradient of R, that gives you R hat, and that is a vector R. So again, so this is equal to 1 minus R hat over R. If you think in terms of quantum mechanics or just a complete set, this is a projection operator. If you can, like you're removing the R hat component from this component. Okay, so that's what it is. So we are interested in vector T dotted with R hat. So apply this out and then the trace, right? So this is equal to T dotted with 1 minus T dotted with R hat times R hat over R. You are interested in the trace. Notice T times 1 is T itself. Trace of that will be trace of T, which I think in one of your homework you evaluated that, right? What the trace of T is. So the trace of T is nothing but diagonal, right? So there is no dyadic nature of it. And trace of this quantity, that's a vector, so you can circulate it, right? So this is nothing but R hat dotted with T dotted with R hat. A lot of properties of dyadics I've used all elementary each step. You've done it in either a homework or we have discussed this before. Make sure you're fluent with all this, right? I like to ask all these tiny steps in a small, like 3-line problem in a test or something. So is that clear? Any questions on that? Overall, what we have done is that we have found the radial force to be. I expected this to go very quick. At cost, like a volume integral of trace of T minus of R hat T R hat over R. Right, dimensionally it's okay because the area has two lengths. This is 3 lengths, but it's divided by R. So it seems clear that we have to first of all evaluate the trace and the radial projections of the flux of momentum, like in the flux being directed in the radial direction. How much is that? So let's go back and so since the flux of momentum has its energy density, let's calculate U once and for all. So we have let's calculate E times D, right? And the trace of that will be U, right? So E times D is equal to epsilon naught E times E. And we are interested in the volume, like when you're actually evaluating this, we are primarily interested in evaluating really on this, because this is mostly on zero, right? If we were really evaluating on this integral, most of this does not contribute, right? If you're doing it on the surface, so if it is zero, so it is right between that contributes. So we mostly are interested in the outside. Inside is zero. So outside, how much is that equal to? Epsilon naught times E. So that's what Q squared. Something. So this is only 4 pi, so that's 1/16. So let me write 4 pi epsilon there. So keep this separate. That's Q squared over 4 pi epsilon naught. Like one of the epsilons cancels out. And this is 1 over r raised to 4. And that is r hat times r hat. Right, that's all that is to it. And this is for right over there. Inside of the zero. I don't even bother to write that. Is that clear? So I did this, multiplied it 2 times, and multiply that with an epsilon naught that cancels out. Yeah, so that's it, I suppose. And yeah, so what is U is half of E dotted with D. E dotted with B is the same as putting a dot there, that becomes a 1. That's equal to 1 over 8 pi times Q squared over 4 pi epsilon naught times 1 over r raised to 4. That's it. Other quantity I need is T, right? So T is equal to 1 times U, which is this quantity U, right? And this is 1 by 2 of T, right? So minus of r hat, and this is something 1 by 2 times U, right? Is that correct? Maybe. Oh, is that right? So maybe write this like this. E and D. That's equal. Minus r hat. That's this. But this whole thing is nothing but 2 times this, so it's 2 times U. That makes it simpler a little. Okay. We can do trace of T immediately. That's equal to taking the dot product here, so that's trace of 1s. Trace of unit dialectic is 3, right? So it is 3 times U minus trace of r hat is 1, so it's minus 2 times U. That's equal to U. And you're also needing the r hat dotted with P divided with R hat. That's equal to 1. So this is the same as R hat divided with 1 divided with R hat times U minus of R hat divided with R hat times R hat divided with R hat times 2 times U. That's U minus 2 times U, so that's minus. This is a important manipulations. This is if you want the construction of the actual term that we have to evaluate. That's specific to the problem. This thing. Okay. Almost there. And there's going to be simplicity because we're doing a conducting sphere. We could have done this for a solid sphere also, as I said, but conducting sphere has the simplicity that everything is zero inside. So that's fine. Radial R is equal to minus doing a surface integral. That's basically we're doing this on the surface of a sphere which has a radius of R at dotted with P, and that's minus of U. Plus, this is a volume integral of, you can say, trace of P is U minus of minus U over radius R. But we should be careful here. Why should we be careful? Because this is over the volume. This is only true for everything of this is true only for R greater than R. Right? When I'm doing this on the volume, most of it is zero. If you're doing an integral over A to B, and you remove a really tiny, infinitely thin element outside, what happens to the integrals? So let's say A to B integral of f of x is, let's say, k. But what is the integral of A to, let's say this is C minus delta plus C plus delta to B of dx f of x? Is that equal to k? Remove a small area out, and the limit delta tends to 0. Are these two the same?
Maybe K minus F of C. Remove that.
K, so this is equal to K minus f of C, then the dimension is not correct. I have to multiply that with the tiny element there, right? F of C times C plus delta, C minus delta, so it is 2 times delta. The limit delta tends to 0. That goes to 0 unless this is infinite. So as far as your function is not infinity, you're sure to get a 0. So removing 1 point from an integral, you're pretty safe. Right? Integration is an area, so if you remove a small, tiny, infinitely tiny element, area remains the same. As far as the function is not infinite yet. Okay. So that's the same thing we are doing here. This is the volume. I'm interested in this tiny hugging place there. That infinitely tiny thing is not going to contribute. If it was a solid sphere, it would have contributed. So this term does not contribute in the case of a shell, because it is right on the edge and it is an infinitely tiny element there. Solid sphere quiz. think of what it will contribute, think. Again, you don't have to in detail, do it. If you look into my notes from last year or something, last lecture somewhere, it is done and it is, you can evaluate that. But for our case, this is equal to 0. Right, because of this argument. Or because delta tends to 0. So this is equal to minus dA of plus times u. This is an integral on the surface of equal radius. U depends only on the radius r. Right? U is only r dependent. But where is u? It's only r dependent there. So there is no angular dependence in here. Remove that. So this is u of r now. This is a closed surface interval, right? On the surface r, and the surface area of that enclosing sphere, that's equal to u evaluated at r times 4 pi r squared. So f of r over 4 pi r squared, which is the definition of a pressure, right? The radial force divided by the area, surface area. That's the pressure on that spherical shell. That's exactly equal to u of r. If there were these terms, there will be a, but this doesn't really go to 0 when it is a solid sphere. I'll encourage you to think about that. And this is equal to 1 over 8 pi 4 pi epsilon naught. As if these are 2 point charges separated by a distance r. Oh, no, it's not really separated by distance r. Because it is per unit area. So it is area that you have to think of. That's the pressure to think of. Or the electromagnetic stress on that sphere. Conceptually, there is a significant difference in this interpretation and the way we interpret the forces point to point. This is from the field. This is the field trying to push it out. The electric field is doing the job.
Why do you say like 0, the volumeter?
This is the volume integral goes from, let's say this volume goes from 0 to r, right? Let's say the radial component alone, plus let's say this is r minus delta and r minus delta to r plus delta dr. Right, and that is a d theta d phi, right, with other terms. Is that clear? Now this is equivalent to this here, and as far as this doesn't diverge at that point C, there's no way it can contribute.
The second integral is r minus delta or r plus delta.
This is r minus delta, correct? Again, what's the question?
Shouldn't it be like 0 to r minus delta and r plus delta to
No, I'm doing the volume, right? So this is the volume. I go from here to here. And then here to here. From here to here, the first one is 0. Why? Because eta d is equal to 0, right? For r less than r, this is 0. Right, so everything goes to 0, u goes to 0, everything goes to 0. So whatever this piece is not going to contribute. So this first of all goes away, then you're left out with this. Right, that's equivalent to this argument, like f of c times 3 delta. It's really tiny and I'm taking the limit delta tends to 0. And as far as this quantity here does not blow up at that point, which it does not because R is fixed, then I'm good. Like R is not 0. If you're under at the center of the sphere, then that is a challenge. But we are outside, so this doesn't blow up. So it has to go to 0. So it's a clean argument. Did I convey that? Not satisfying.
This part.
Oh, so you didn't understand this part.
K minus.
Okay, here, let's do this better. Okay, so this is clear, right? That's equal to, think of here. If this shaded region was not there, that's K.
Yeah.
So this is equal to K minus the area of this shaded region. In the extreme limit where this is thin, that's a rectangle. So the height of that is f of c times the width of that rectangle, which is c minus delta, c plus delta, so it is 2 times delta. Yes, is that clear? I'm taking the limit delta tends to 0. So this is a number 0 multiplied by, what am I multiplying it? And 0 multiplied by something can give you a finite number or non-zero number only if this is infinite. Or this has to be 1 over delta, that's what I think. But 1 over delta is like 1 over 0, but it's not, right? This is not 1 over 0 when R is. So this is pretty much a compact number, like a non-zero number. So since it's a non-zero number, that's a non-zero number multiplied by a very small quantity, it will go to 0. Right. So one has to be worried about that. That is there such a quantity? Sometimes, very rarely, it's there, and that's becomes non-trivial. Then, but there are systems where we consider those.
So that argument makes that zero.
Makes that 0 exactly. Okay, good point. And then everything falls. This argument is not necessary in a solid sphere. And what I'm encouraging you is to try to do that for the solid sphere. Right? We know the electric field for a solid sphere, figure that out and then go through it. It's just a matter of going through that integrals. It's relatively easy integrals. And then there is an added piece to that. This changes this, just a number changes there in front. That's nice. I'll stop here.
So,
Yes, please, fine.
so the quiz is just go over that.
Yeah, go over this and then it's a quiz. It is not, you just have to qualitatively go over it. It's there in my notes from previous years. You can just go through it and just give it a thought. What's the changes that happens?
Okay.
It's a good extension to the problem. That's the way to put it. And I'll limit myself to these examples and we will proceed to the next topic.